Okay, good evening, everyone, as you all file into the virtual room as it is. Welcome to week 2 of our short course on IT fundamentals or IT basics. We're a little bit early. We're just opening the floor and letting everybody come in. So what we will do is we'll return in about 5 to 6 minutes and introduce our mentor for the evening. And in the meantime, maybe in the chat, you can say hello to us. Remember to set your chat to everyone. And say hello to us and tell us where you're from, and we'll have a bit more chat in a couple of minutes. But welcome again, and speak soon. So as I mentioned just before, everyone, welcome to the second and final webinar. As Lily is just typing out, my name's Shane Murphy, and I'm your host for this evening. We're just giving everybody else a couple of minutes to file in. So don't worry about the sound. There is sound. If you can't hear me now, then that's a problem. But everything is going well, and I can see there's people from all over the world tonight. There's people from Poland, Kenya, Liberia. Somebody, I could swear somebody just put the Shire. Yes, from the Shire. Which one? Sutherland, maybe. Portugal. I'm interested. It's very hard, I think, sometimes to get people from places in the, what would you call it, the more western part of the world, South America and America at this time of day, because it's about, I think, 4 a.m. their time or something ridiculous. So it is very hard. But Mumbai, Sierra Leone, great to see you all coming along. And I think we're probably getting close to starting. So just give us a couple more minutes while we let more people log on. It's only 7:32 at the moment. We're not demons for time any at all, particularly as it's in Australia, at least summer, and we're all very relaxed. It's been a warm day here in Melbourne. I know there's bushfires in Queensland and other places, and it's generally warm around the country at the moment. But there you go. I hope everybody is at least safe and well where they are, and thoughts go out again as last week to all the people in Turkey and Syria and people who know and have family in Turkey and Syria from the big earthquake that happened there a week ago. It just seems to be worse and worse news recently. So we're certainly thinking of them at the moment. I'll be back in about a minute or two. Yes, Ray, exactly. Thank you for reminding me, and thoughts to New Zealand too, which is there's a big cyclone the last couple of days in the North Island. Okay, there's nearly a couple of hundred people here, 160 odd. Let's kick things off. This is, and I'd like to welcome you formally to our second webinar in IT basics. And this week we're going to talk about networking and cybersecurity. Our mentor tonight, as you probably already know, is Matt Constable, and he's one of our long-standing, long-serving mentors whose idea this course was, because he's had a number of people come into his subject saying, oh, what is this thing called a PC? Because we do a lot of courses now that don't require a deep knowledge of IT that we have historically had. So this is designed as a course to just give you some of that background so that when you come in to do a postgraduate study with us, then you've got an idea of what's going on. You don't have to worry too much. It's also a good introduction to learning online and doing some of our courses, because Matt is one of our mentors that teaches quite a number of subjects and has for many years. And he talks about the sorts of things that you'll need to know. So you get to understand the way that we do things here, as well as just in itself get a damn good course on interesting and fundamental topics in information technology. Now, there's, as always, a little bit of housekeeping to go with tonight before I formally introduce Matt. We encourage questions, and we encourage you to put proper questions, as we call them, into the Q&A section. Things about, that you might want the mentor to answer for us. Things about the housekeeping when the recording's up, all that sort of stuff. Kit and Lily, who are both here tonight doing the moderating, they will keep sending you links and information about where the quiz will be, where the recording will be and when it'll be available, all of that stuff. But we do really would like you to ask questions and interact with each other in the chat. Remember to set your chat to go to everyone if you want us all to see it, or if you want everybody else to see it. And yeah, as I said, it would be remiss of me to not remind you that, you know, this course is particularly suited to our students starting off in the grad certificate in computing career transition. That's the course that we run for people that want to get into IT with no IT background whatsoever. It's designed to help you hit the road running and get stuff going along. But really, that is enough of me blathering on at this point in the evening. And I would like to welcome at this point, Matt Constable, and it's good to see you back again, Matt.
Thank you, Shane. Thank you for that introduction. Okay, everyone, welcome back to those who attended last week. And if you weren't able to attend last week, welcome for this week. So tonight is going to be probably run a little longer than the hour that we've set aside, but I'll try to keep things as streamlined as possible. But the reason we're doing that is because we are covering an introduction to networking and cybersecurity at the same time, rather than just our IT fundamentals. There will be components of this that will sort of build on what we looked at last week. So if you haven't been able to watch the recording or you're unable to attend last week, there might be, you might find it a little difficult in a couple of spots. But for the most, both of these sort of subject matters will stand alone in isolation. So with all that said, let's progress and get into the nuts and bolts of it. So the agenda, first of all, is we're going to look at networking for a start. So what are networks and why do we use them? Some little discussion around different topologies, technologies that are used to build networks, some very simple IP version 4 addressing. We won't be going into IPv6. I don't know that there would be many coming along for an IPv6 session. IPv4 is boring enough without adding v6 into the program as well. So we'll go over some very simple addressing just to give you the basics of what you need to understand to make sense of some of the subjects that you might encounter if you were to enroll in a grad cert or in other areas of your business or work life. And we'll also look at some fundamental concepts around routing and switching, so the two main devices and components of a network. And then in cybersecurity, we're going to look at some basic cybersecurity concepts around design, around host and network security, and have a look at some common attack categories or vectors. So let's get started with the networking. So networks are basically used as a resource to provide multiple users access to some type of system in a nutshell. So network services are the resources a network makes available to its users, and this includes applications and the data provided by those applications. And there are sort of mostly two types of networks that we talk about in terms of class of networks. So we talk about client server networks, which we briefly touched on last week, and that involves having a whole bunch of clients, so PCs or laptops, connected to a shared repository of information, so a data store, if you like. So that's typically might be stored on in simple networks, stored on a single server. And all of those clients will interact with that server to get that information. So instead of everyone having to have a copy of that information on their own laptop or desktop, it's on the server and everyone will access it through that. So it's a shared environment. But in terms of the other applications that are also available on networks as well, there are, as we said, the client server ones, which are around things like our word processors and our spreadsheets, our databases, our customer relations systems, any sort of workflow systems that we use, change management systems, those sorts of things. There's also typically file and print services. So that enables you to be able to get access to files, different files. So whether they're Word documents or Excel documents, or whether they're photos or other files that you may, PDF files, for example, might be another example of things you might see there. And then also providing you with the ability to print. So print to your multifunction devices, to print to traditional type printers, to print to a print to email type system as well, so that you can have a document, print it out, and send it out via to like a fax to email type service. There's also communication services. So that falls into things like, so we're not talking about email there, but we're talking about mainly video conferencing, voice conferencing, or IP telephony. So using soft phones or hardware phones that use your network traffic. And while there are other types of applications that are also found on networks, these are the fundamental primary ones that we're going to talk about in this particular course. So file and print servers, file and print services are generally offered by one or more servers. So in smaller organizations, you may have a single server that does the file and print services as well. So it will host both all the file storage and it will connect the users to the printer as well. But as you get to larger networks, you'll branch out into more and more servers, and you'll start to have, you might get to a point where you have, you might have a dozen or more file servers, and you might have a dozen or more print servers to service all your different customers and clients. And there's lots of different ways to set them up. So you could have them all in the one area, in the one data center or one building, or you could have them spread out all over the place across a wide area network. And we'll look at that in a little more detail when we get to that particular part of this evening's talk. But basically, file services are a server's ability to share data files and disk storage space, or some type of storage space, whether it's traditional mechanical disks, solid state devices, or other network attached storage. So literally big banks of disks that are connected directly to a network point rather than being, or series of network points rather than being connected to a server. A server that provides file services is simply called a file server. And a server that provides print services is called a print server. And if you have them both together, it's just called a file and print service. There's nothing too difficult about that. The print services are simply what gives the server the ability to share the different network attached printers across the network. Now, in smaller organizations, the printers may literally be connected to the server, but in larger organizations and in most contemporary organizations, we will have printers that are actually directly connected either to a wired network or a wireless network, and the print server will help share those resources around to everyone that's connected to the network. Communication services are where we start to talk about a thing called convergence. So convergence is simply a concept which describes the ability to use the same network to deliver different types of communication services. So one might be file and print, okay? So that's your data services, that's your pure data. And then you'll get to audio and video, which are, yes, they're transmitted still as ones and zeros via the same cables, but they have to have assigned to them a different priority of service, otherwise things start to break down. So unified communication is then a term we use to refer to the way that the multiple network-based communication systems are centrally managed. So we might have a number of different servers, one for file and print, for example. You might have one for your IP phones to connect to. You might have one for your video conferencing systems. And so together, they will be managed as part of a unified communications platform. And there's lots of those around. There's some really big corporate enterprise type unified communication systems, which the likes of Cisco, for example, with their unified communication managers and contact center products that they have for really big organizations. There are smaller organizations that might use something like Microsoft Teams, for example, as a unified communication collaboration platform. And there's lots of other different variations of those across the world. So the three types of main communication services, though, in a unified communication platform are conversational voice. So that is turning normal voice into an IP connection, which is effectively what we're doing here via my headset. You can hear me. My voice is obviously not digitized coming out of my mouth. It's digitized as it goes through my laptop, sent across the internet via Zoom to you, and then it's converted at the other end through your speakers or headset or whatever it is you're listening with. And that then, so that's conversational voice. We have streaming live audio and video and streaming stored audio and video. And really the only difference about that is that obviously one is live and it's being recorded and sent out at exactly the same time, whereas a stored audio and video is something that's been recorded and is streamed off a storage device. Now, what's the next important part we need to understand is the different network models that exist and some of the key terminology that describes a network model. So the term topology really describes how parts of a whole network fit together. And we'll see that on the next slide in a little more detail. A physical topology mostly applies and describes the hardware and how the computers actually physically fit together with cables between them, or some sort of cabling system between them. So it's actually describing the physical connection of end to end across the network. The logical topology is more about how the software inside the switches and routers works and describes how access to your network is actually controlled. So if we look at this particular picture here, and this is a descriptive of a more of a logical topology than physical. These lines here in between these hosts represent communication channels. So while that logically may look like this, so in this case we've got a mesh system because we're using a peer-to-peer architecture as compared to a client server. So while this may look like that's how the network would fit together, the actual wiring of it and the physical connections may be actually quite different. And I might actually just draw that, probably rather poorly, but on this graphic in a second. What's important about this in terms of talking about client server and peer-to-peer architecture is a client server architecture. This one here, as we described last week, we have a this one's called a sender because it's using laptop depictions. But if we consider this particular host at the top to be a server, all of these other devices connect to that server in order to get access to that server's information. Okay, so that's a client server. We have 4 clients and a single server providing them with information. In a peer-to-peer architecture, there is no such thing really as a server. In this case, all devices will send communications directly to each other. So if we think about this client-server architecture, if this device here, device A, wants to communicate with device B, in this sort of deployment, it would go through the server. Now, that's not always the case, even in client-server model land. Hosts can talk directly to each other if they're not participating in a client-server application discussion, so to speak. So they can still talk directly to each other, but in terms of the interaction with the applications, it will go back through the server for them to be able to just talk to each other. In a peer-to-peer architecture, that doesn't happen. So all of these devices here can speak directly to each other. So what we end up with is a lot more logical connections and a bit of a mishmash of wires and, well, not necessarily wires, but communication protocols and lots of noise in our network, whereas here it's much more streamlined. So if I was to draw now how that might look physically, what you would more likely than not see is this sort of arrangement. Okay, where you'd have a device in the center of your network, most likely a switch, and then each of these devices would connect into that particular switch. Apologies for my very poor drawing. It's actually not bad for me. So that would be those red lines, those red squiggly lines would now be a representation of the physical topology. So this being a switch, so if I write S for switch on it, there's your switch in the center of your network and all your server, so this guy here, plus all of these hosts would connect physically to that switch. And so you end up with this type of physical topology, which is known as a star, okay, because of the way it looks like the center and all these rays of light radiating from that star. The same could be true with the peer-to-peer architecture as well. So you could also have a switch here, and physically, they're all connected thus, like this. So it's exactly the same topology. So the networks look identical, but the logical topology, that is the way in which the devices talk to each other, is very, very different in both cases. So that's a representation of the difference between physical and logical. So they don't always match. In fact, rarely do they actually match. So the advantages of peer-to-peer versus client-server. So the advantages of peer-to-peer, so that's this one on the right, is that it's simple configuration. Why? Because all you've basically, let's take physical topology out of it for a minute. If we have a group of workstations, Windows laptops, Windows devices that want to talk to each other, we can simply turn on their wireless network cards, get them to see each other, and basically start sending information to each other at the snap of a finger without having to do a whole lot. They will auto configure their addressing. They'll be able to see each other. You'll be able to start sharing files and trading communications. So it's really, really simple to configure. And it's less expensive when compared to client server, because you don't have to buy an expensive server, and you don't have to worry about buying special licensing for special network operating systems, and you don't have to create user accounts on the server. You don't have to manage all of that side of it. So we simply have a peer-to-peer network where everything can talk to everyone, all the information is shared, and everyone's happy. So it's simple, easy to configure, and cheap. However, the disadvantages are it's not scalable. So if you can imagine this picture here, if you had 1,000 workstations all trying to talk to each other, so every workstation you had could talk directly to every other workstation to get information from that. So it would be a mess in terms of trying to manage that, in terms of trying to scale it to an enterprise level. Whereas client server, you could have, as your network grows and you get more hosts attached to it, more laptops and desktops, once it gets past the capacity of your server, you can simply add another server. But you only need another one for a little while until you outgrow that, and then you add another server. So instead of trying to manage this huge amount of communication traffic, you can simply add servers to the building block and scale your network that way. So it's easier to scale client server than it is peer-to-peer. Peer-to-peer is also not necessarily secure. Most of the although you can set up secure protocols between them, in typically out of the box, that is not the case. And so it becomes a case where an intruder, for example, could come and sit on the edge of this network and still see all of this communications traffic. Okay, because everything's sharing to everything. In this case here, with a client server architecture, you've got your server set here with all your user account set on that. If the intruder doesn't have a user account there, it's more difficult for them to get access to that. Not to say it's impossible, it's more difficult. And largely, of course, is the peer-to-peer is not practical for those large installations, which simply ties back to that whole point of not being scalable. So from that, we also end up with a number of different network types. Okay, so we can have personal area networks. So you'll notice with these, all this terminology they end in AN, so area network. So a personal area network is something that would use Bluetooth or infrared. So infrared we don't tend to see too much nowadays, not in communications equipment anyway. We use it with televisions and DVD players and those sorts of things, or roller doors, but we don't tend to use it with communications equipment anymore. Bluetooth, however, is everywhere. So Bluetooth is on every smartphone, it's on every tablet, it's on most laptops now. So you can connect, for example, a Bluetooth headset or a Bluetooth keyboard, a Bluetooth mouse, all sorts of different things to your Bluetooth networks, but it's called a personal area network because it's only very short range. So Bluetooth signals via standard won't usually go more than about 5 to 10 feet from the device you're controlling. So if you've got your Bluetooth keyboard and you take it with you and you're 20 feet from your desktop, you probably won't be able to type anything on the screen. And more to the point, if you could see it, good luck to you, because I certainly couldn't. So personal area network, very small area. Local area network is probably the most commonly known and understood, and this is what we call networks, the business networks that connect workers to a client server network usually within a building, or usually within a single building, even if it's multiple floors spread across multiple floors. Sometimes it might be between multiple buildings if they're very close and you can get your cabling within standard distances connecting the two buildings up. So local area network is what most of us will have encountered in our business, school, whatever sort of life. The next biggest one is a wide area network. So this is typically used by really large businesses that have sites that are separated by very large geographic distances. So it can be as small as 5 to 10 kilometers, or it can be as large as many thousands of kilometers, so literally spanning the globe. So it could be across from one side of a city to another, from city to city, from state to state, or from country to country. Campus area network is sort of a combination of, or sits in between local area network and wide area network. So a campus area network, if you think of like a university campus, where you might have a dozen or so buildings on a very large plot of land, and you need to have communication services between them. So the networks within each of those buildings are termed local area networks, but the network that connects the buildings together is known as a campus area network. And then generally, if you were to say campus area network, you would also be able to refer to all of those interconnections, whether they're within the buildings or between the buildings. And then the last one is that we talk about, and there are others, but these are the main categories. There is a metropolitan area network. Now, a metropolitan area network is normally something that's provided by a service provider. So it's not typically owned outright by an organization unless they're very large. And what this does is this is like a sort of a step in between a campus area network and a wide area network, but it connects multiple buildings or multiple sites within a metropolitan area. So typically within a CBD of a city is what we normally term it. And that's often used, they connect those buildings with very high speed links. So in terms of speed and capabilities, personal area network is very low speed. All we're doing is using mice or keyboard, that's about it. Local area network is high speed, so it can be up to, realistically, usually gigabit speeds. There are some local area networks, there is the ability to go to 10 gigabit speeds in some circumstances if you've got the money and the need, but there are very few people on this planet that would need a 10 gig network connection from their desktop to the core of their network. That would be pretty unusual. Campus area network are high speed because we're connecting buildings together. So there's the likelihood that lots of traffic from each building will be traversing across those links to go to opposite buildings. And so that needs to be more high speed. Wide area network is a little bit of an anomaly because it can range from quite low speeds when compared to local area networks to quite high speeds, but still low speed when compared to local area networks. Although there is the ability now to get 100 meg plus wide area network links, typically that's not the sort of speed that you're going to get. You might get 20 or 30 megabytes, for example, or megabits per second across your wide area network link. And then your metro area network is again very high speed, typically fiber, so run across fiber optic rather than copper cable, and it's multi gigabit, potentially higher speeds as well. And that's simply because it's infrastructure or cabling and resources that are shared by multiple buildings and lots of different users. And so the requirement for speed is much higher.
Can I ask a quick question?
Of course you can.
Something just occurred to me while you were talking about megabytes and megabits. And I don't think that's something that we explained earlier. And it's always, a lot of people I think get confused between megabit speed and megabytes.
So big B, little b. And that's actually a really good point because that actually went through my head as I said it as well. So thank you for that. So I might just hold on to that for a minute though, until I get to the IP addressing, because I think it'll be easier to blend that in with that. So I'll make a note of that and I'll talk about it then, but that is a very good question. So thank you. Okay, so physical topologies. These are basically the physical topologies that we traditionally talk about. Not many of these are actually typically used in the contemporary world. So we had the first one, the original one that we had many years ago. The two main ones that we used to use were bus, where we had a single communications line, and it was literally a black cable that would run through your office underneath your desk space and through the walls, and all of the PCs and laptops, although mainly in those days it was PCs, would connect in via these small dropper cables into that backbone cable, and that was known as a bus. So the red cable there signified that represents the actual bus, and all the traffic would across the network would flow across that particular bus. I'll skip across star for a minute. Ring was another topology that was used very early, and as you can see, just all the computers were connected in this ring configuration here. That again was an early common one. Unfortunately, as interesting as it is, because it is really fascinating, it's outside the scope of what we want to cover here tonight to talk about the communications protocols and the intricacies involved in both of those, because it's a really interesting conversation. Legacy, albeit probably not all that useful nowadays, but certainly interesting to an old networker like myself. The star topology is the most commonly deployed now in local area networks, where you have a central communications device, typically a switch, and all of your devices will connect back to that. And that can be extended and extrapolated out to have multiple switches, multiple hosts, but eventually they all come back to this star topology or multiple star topology. A mesh is a topology that's not typically used in a local area network, but it is used in a wide area network. So in this case, these desktops wouldn't be desktops, they would be replaced by routing devices, and you would set up a mesh between those routers, which one router per site in your network, and all of those sites would then have redundant links to every other site because of this mesh topology. A tree topology is one that I don't think I've ever actually encountered in the wild, unless it's been inadvertently set up. It's generally not a good way to do it, and certainly not in this representation with PCs as being the central connection point into the bus down here. Normally these would be switches or routing devices, in which case we sort of separate the topology again. And then the last one is point-to-point, which you might use in very small networks, but not typically in an enterprise network. So then branching on from that, now we need to, okay, we've got a bit of an idea about the physical topology, about the logical topology. So we understand that the way in which something might be physically cabled may not necessarily be the way replicate the way in which the traffic or the logical topology exists. And so we now get to the point where we need to start understanding what the simple network hardware is that builds things together. And as I was saying before, see, tree topology, not really something we would use, not in this sort of setup. But if we look at this here, you might say, well, that looks a bit like a tree, Matt. What are you talking about? What it actually is, however, though, is two star networks connected by a router. So this is what I was saying before. You can have individual star networks. So here's one here and there's one there. And we just happen to have this routing device connecting the two together. But in terms of the physical topology, regarding looking at it from the point of view of where the center of each of these networks are, where we've got a star network. So we've got two stars connected via router. So you might think it looks a little bit like a tree, but not really, because we're now using network hardware, network devices to connect our computers together rather than computers. Let's face it, that's what these guys have been specifically made to work with and to operate as. So that begs a question, what is a switch? Glad you asked. So switches, and here are some examples of them. These are a bit old, so these are Cisco switches. So many of you have probably heard of Cisco systems. They're probably still the largest vendor of networking hardware on the planet. But really what they make is they don't actually make hardware, they actually make software. They actually make internetworking software called the Internet Working Operating System, iOS. Now, some of you may say, hang on a minute, that's Apple's operating system. No, it isn't. It's Cisco's operating system. They found it first, and Apple had to pay them to use iOS for their operating system as well. So the original iOS internet working operating system is from my old friends at Cisco. Now, these devices here are quite old. And they obviously they're different size for different size networks and different types of networks. So we've got the little ones here at the front, which might be used for a small office, home office, or a very small business. And then we've got these switches here. So there's 4 in that stack, 4 in that stack, and there's 5 in that stack. They've got different amounts of ports in them, different types of ports. They're very configurable. They can stack together. So these 4 switches here will appear as a single switch. You can configure them so they look like one switch. And they have bucket loads of features, unfortunately, which are way outside the scope of what we need to talk about tonight, but there are lots of different things that these things can do. These 2 big guys at the back are what are called chassis-based switches. They are a very large piece of iron cabinetry, basically, and inside them they have the ability to take all these different line cards, which have lots of different features on them. So these ones are primarily filled with switching cards, but they can also come with a lot of other cards as well that can do many, many other things. As I said, these are a bit old. These are some 6500 series switches. So they're quite old now. Well, that one might be an 8500. And these things up here are the power supplies, but I digress slightly. So the switches are connectivity devices that divide or subdivide a network into segments. So if we go back to this here, we can see each of these blue lines to each of these devices is considered a separate segment. Okay, a separate physical segment. And that's the job of a switch, to break our network into separate physical segments, mainly for the treatment of traffic. So the efficient treatment of information as it flows across the network, rather than just having it blasting out all over the place. Switches work primarily on what's called a hardware address, which is a hexadecimal address, literally 12 hexadecimal digits, and that exists on your computer and or your connected device, so your laptop or your desktop, and it uniquely identifies your device in theory. And I say in theory because there are so many millions of devices connected around the world now that not all of them are going to be unique, but that's a theory, that they are sufficiently unique that you're never going to have 2 with the same address on the same network, which obviously, if you have a room full of people and 10 of them are called Matt, that is confusing until everyone works out who's who in the zoo. In a computerized system, that's even worse. If you've got 10 desktops and they've all got the same address, that makes it very confusing. And so the poor old network doesn't know who it's going to talk to, who it needs to talk to. So it's very important that those hardware addresses are unique. Some common switch components include, a bit like a computer, they have an internal processing unit. They run an operating system, in Cisco's case, iOS. They have memory, and they have these ports, which you can physically plug your devices into. We then have our routers, which are these particular devices here that sit at the center of our network. And these are, again, multi-port, so they have lots of different ports. We'll see some pictures of them on the next page. And what these do is they direct data between network nodes. And that's really just a fancy, complicated way of saying they work like an electronic digital roadmap. That's what they are. So you can have, if you think of a roadmap, if you're sitting in Melbourne and you want to get to Echuca or Mildura or Sydney or wherever you want to go, you look at the roadmap and you see along the way towns along the road that you're traveling to get to your destination, right? So each of those towns is analogous to a router. When you get to that town, there might be only one way you can go to get to your final destination, but there might also be multiple ways you could go to get to your final destination, because you might decide, well, I'm going to take a bit of a detour here and I'm going to see that mountain range or go fishing at that river before I go to my final destination. And so a router is really just a digital roadmap. These guys also integrate or provide the cutover or the differentiation point between a local area network and a wide area network. So different network types, so local area network, wide area network, campus area network, metropolitan area network, do not generally interconnect with each other all that effectively. So you have to have some piece of hardware in between that will connect them. And often that is a router, particularly in the case of local area networks and wide area networks, you put a router in between them to not only control the traffic that goes across those routed links, but also to translate between the different physical types of interfaces that you might have. So you might have copper on one side, in which there are many different types of copper interfaces. And on the other side, you might have fiber or wireless or some other type technology. And so the routers have the ability to translate them, not just logically, but also physically as well. And so as a roadmap, they direct data from one segment or network to another. They don't work on hardware addresses, they work on IP addresses, which we're going to look at very shortly. They are protocol dependent. So what that means is if you've got if you're using IPv4, so if you're using IP addressing on your routers, okay, you have to have the software and the configuration that is dependent for that particular protocol. And in most cases now, really, there's only IPv4 and IPv6, version 4 and version 6. There were other older protocols that we used to use in networking many years ago, but most of them have now gone by the wayside. The thing about routers is they're slower than switches, so they can't transfer traffic as quickly as switches. And that's because they have to look further into the communications chain, into the traffic that's going across the network in order to interpret where it needs to go. So they need to do more work to get from one place to another. Here's some examples of some routers. So these are Cisco, Juniper, and Huawei, are three companies that are big in the router market. And these are some more Cisco routers over this side. So these are smaller, sort of satellite site, maybe core routers in very small networks, and these are some larger ones. Now, those of you who are a bit eagle-eyed may say to me, hang on a minute, those routers down here look exactly the same as the switches we looked at before. And indeed, you are correct. These devices here can act as both. So they can be a switch and a router as well. So there is a capability to do that with these devices as well. The more money you spend on them, the better feature sets you get and the more connectivity you can run through them. All right. Now, this is the fun part, okay? IP addressing, and we'll talk about megabytes and megabits here. So IP addressing in 10 minutes, hopefully less. It's complex. It can be a pain in the backside to learn, but it is a very valuable skill you can have, particularly as a networker or as a security person. There are some tricks that you can learn, and they are varied. You'll pick up a couple from what I'm going to say, and there's some resources on Moodle that you can pick up some extra tips for, but you will come across lots of people in your working life who will have lots of different ways of doing it. None of them are wrong, they're just different. The main thing with IP addressing is you have to practice, practice, practice in order to get it right. And even now, after nearly 30 years doing it, I still get it wrong sometimes. So IP addressing, what's it all about? Well, it's about logical addressing. So that is providing a hierarchical structure. So I like to compare IP addressing to like a physical address system. So you think about street number, street name, suburb, city, state, postcode. Okay, that's a little bit more extensive than IP addressing. But IP addressing basically has two ways of doing it. So it comes with a network ID, which identifies the network. So the network is analogous to a street. And the host ID uniquely identifies the actual device that's connected to that network. So that's analogous to the house number. So network ID, street, host ID, house number. Now, in both cases, these can be set either automatically by certain protocols. There's certain systems in network systems that allow you to automatically assign the IP addresses, or you can manually assign them yourself as a network administrator. Depends on what you're trying to achieve, whether you do one way or the other. Automatic, a lot easier. You have less control over it once you actually implement it, but it's really easy to implement and get addresses out there. Manually assigning, a lot more overhead in managing it, but at least you always know 100% what's going on. And in most networks, you'll have a combination of both. So your servers and all your network equipment will be statically assigned an IP address, and then your desktops, workstations, laptops, phones, tablets, those sorts of things will get an automatically assigned address. Common protocols, in fact, really the only two you'll see nowadays, IP version 4, which is just referred to as IP, and IPv6. There are some address classes, which is sort of important to get your head around. I'm not going to spend a lot of time explaining it because we've got to get on to other things which are more important. But what is useful for you to understand is the information in this particular table, particularly the first column, and the number of networks and number of addresses, these two columns here, and then the start and end address. Happy to take questions on that at a later time or through the discussion forums, but I'm not going to spend a lot of time talking about it now because it literally could send us down a very deep rabbit hole. There's a couple of special range addresses. This particular range here is your loopback range. So a loopback range is what you use to test to make sure that IPv4 is working on your device. If you can't get access through that network range, then your device is not working correctly. And then this range here is one that's used by a protocol called automatic private IP address, IP addressing. And that's used by most Windows machines in order to set up a peer-to-peer network, okay? So remember before we were talking about having a whole heap of desktops or laptops talking backwards and forwards to each other. This is the way they can easily do it because they use this automatic private IP addressing. As soon as you turn the device on, if it can't get an address from anywhere else, it will automatically assign itself one and it will start communicating with anyone else within distance that will listen. So the first basic you need to understand for IP addressing is binary math. And it's quite simple. It's either a 0 or a 1. So an off or an on. Okay, so in decimal, we have values 0 to 9 in each column. In binary, we have 0s to 1 in each column. And similar to decimal math, we start from the least significant column being on the right-hand side. So the least significant column is worth 1. The next column is worth 2. The next column is worth 4. The next column worth 8. The next column is worth 16. So hopefully you can see a pattern. It's to the power of 2. So 0 to the power of 2 is 1. 1 to the power of 2 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8, so on and so forth. Okay. Now, typically in an IP address, so now getting back to the megabytes and megabits. Now, a bit is one of these characters here. So a 0 or a 1 is a bit. So that particular field there, that's a single bit. If you put 4 of them together, that's called a nibble. Okay, it's a bit of trivia for you. You'll probably never hear that again, but it's called a nibble. If you put 8 of them together, so 1, 2, 3, 4, 5, 6, 7, 8, you have what's called a byte. So a byte is equivalent to 8 bits. So the difference between a megabit and a megabyte is that in round figures, a megabit is 1,000,000 bits and a megabyte is 1,000,000 bytes. So it's 8 million bits, and that's just in round figures. That's not actually 100% correct because we're using base 2. We're using binary, but in round figures, that's what you can equate it to. So a megabit is 1,000,000 bits. A megabyte is 8 million bits because it's 1,000,000 bytes, each of which have 8 bits. So that's the difference. So when someone says to you, we're going at 1 megabit per second in terms of network speed, okay, that's 1,000,000 bits per second it can transfer. If they said they were going at 1 megabyte per second, that's 8 million bits it would be able to transfer in a second. So that's the difference between those. And the nibble is the 4, so, but you won't hear mega nibbles. I've never heard mega nibble anyway. It's probably something I'll start using from now on, but it's not something you would typically hear. So that's your basics of binary math. So each column doubles in value. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So each one of, if you then looked at this value, where there's a 0, that indicates that we're not going to use that value in that column. Where there's a 1, we are going to use the value in that column. So if you transpose all that down to the values and add them all up, we have no 1s, no 2s, we have 1, 4, 1, 8, 1, 16, no 32s, a 64, a 128, a 256, a 512, and a 1024. And if we add all those together, you get a total of 2012. So that's what this binary number here, 11-bit binary number, represents in decimal, 2012. So it's a bit easier to read that, isn't it? But again, it's simply because that's what we're used to. However, IPv4, it's useful to know that binary math because it allows you to translate backwards and forwards and allows us to do what's called subnetting, which is really important in segmenting our network up into more bite-sized chunks. An IP version 4 address is 32 bits long. So that's 11 bits, so you can imagine how long it is. It's actually this long down here. There's an example of an IP address there. What you'll notice, however, though, is there's a full stop in between every 8 bits or bytes, okay? They can also be called octets because there's 8 bits in that little bit there. So it can be called octets. Generally, we call them bytes. So an IPv4 address is 4 bytes in length, and it provides 4,294,967,296 unique addresses, which sounds like a lot. But when you consider how many devices are connected to the internet and you consider the rise of the Internet of Things and the Internet of Everything, then that's really not that many addresses. Now, to make them friendly to us as humans, we write them in dotted decimal. So what we effectively do is we take each of these bytes in binary, which is what the routers and switches and computers use, and we simply turn them into the decimal representation using that numbering system there we just spoke about. So because they're easier for us to remember, we're more likely to remember the dotted decimal than we are binary, simply because that's what we learn as children all the way through. So each number, as I said, is called an octet, composed of 8 binary bits. If we looked at this address here, 192.168.0.1, this is what it looks like in terms of binary, okay? So then to do a decimal to binary conversion, the easiest way is to simply memorize or write down the following column headings. So we go from right to left and we write our base 2 numbers. So 1 for our first column, 2, 4, 8, 16, 32, 64, 128, doubling in each column. We then use the column headings in combination with the decimal number to convert to binary. So in other words, if we want to convert from 172 to binary, we do it this way. We start from the left-hand side and we say, all right, is there a 128 in 172? Well, yes, of course there is. So we know that 128, the 128 column is present. So we put a 1 there. We then have a leftover, I always mess this up. We then have a leftover of 44. So we go to the next column. How many 64s are there in 44? Well, there are none. We can't make 64 go into 44. So we know there is no 64 value column required. So we put a 0 there. We then go to the next column. Are there any 32s in 44? Well, yes, there are. So we know that that column is set to a 1. And we now have 12 left over. We go to 16. 16 doesn't go into 12. So that column is left as a 0. We still have 12 left. We go to our 8s column. There's an 8 in 12. So we turn our 8s column on and we're left with 4. We then go to our 4 column and there's a 4 and 4. So we turn that column on and then we have nothing left. So our last 2 columns must be 0 and 0. So therefore, 172 is equivalent to 10101100 in binary. And clearly, if you can go one way, you can go easily the other. So that's simply by looking at the columns that have a 1 under them, finding their decimal value and adding them all up together. And then you can go back the other way. Now, the next thing that confuses people, and I don't blame them because it is confusing sometimes, is the subnet mask. Now, remember I said before you have a network ID and a host ID in your IP address? Well, the subnet mask is a thing that tells you which one is which. So it tells you, so if you were to just to look at that number 192.168.0.1, you would have no ability to understand what is the street address, for example, or the network, and what is the host address or the street number. The subnet mask is what gives you that clarity. Now, in this case, we have a subnet mask of 255.255.255.0. So effectively, that's all ones, 8 ones, 8 ones, 8 ones, and no ones in binary. So we've got 24 of our 32 bits of the subnet mask in ones. That can also be written as /24 in what's called slash notation. So this is dotted decimal notation. Slash notation is where you simply count up the number of ones in your subnet mask and you write it as slash however many number that is. So in this case, the full address and mask for this device would be 192.168.0.1/24. The subnet mask has two rules. If a bit is set to 1 in the mask, the corresponding bit in the address identifies the network. So that then becomes a network ID. If the bit is set to 0 in the mask, the corresponding bit will identify the host or the street number. Street number. And I'll show you an example of that in a minute. So subnetting then is the creation of new networks or additional networks by borrowing bits from the host portion of the subnet mask. Okay, so we don't borrow it from the network portion, we borrow it from the subnet portion, from the host portion. The caveat is with this, the more networks you have, the less hosts you can have on each network. So consider this network here, 192.168.254.0 with a 24-bit mask. Now we can use this third part of the third octet in the subnet mask. We can steal some bits from that to use for more networks rather than for hosts. Or alternatively, we can even go down to this fourth octet as well. So bits can be borrowed from the highlight portion to create more subnets. If we shift our ones to the left, so if we think of a binary string of digits from left to right, if we shift the ones, the consecutive ones to the left, we get more hosts but less networks. If we shift it the other way, we get more networks and less hosts. But let's just keep it really simple for the moment. So if we have a quick example, 192.168.200.33/24 is the address that we're given. So the IP address is the 192.168.200.33, and the subnet mask can then be expanded out from /24 to 255.255.255.0. The question is, we want to know which part is the host ID and which part is the network ID. So which part is unique, which part delineates the actual device itself, so the desktop or laptop, and which part describes the actual network that it's on. And the way to do that is we cut it up into binary like this. So this is the address 192.168.200.0.33, sorry, not .0, .33, written in binary. If you don't trust me, work it out with your column headings. Remembering though that each colored section of 8 bits, you have to restart the column heading. So that's column 1, 2, 4, 8, 16, 32, 64, 128, and then we go back to 1 again because we're in a new octet. So you consider each octet separately. But it is, you can trust me, I think. Yeah, you can. Then underneath we have the subnet mask. So we've got 24 consecutive ones and then we've got 8 consecutive zeros, which is what we said is a /24. So then we have to remember the rule. So if there's a 1 in the subnet mask, the corresponding number in the address is part of the network ID, right? That's the rule. And if it's a 0 in the subnet mask, then that corresponding number is representative of the host. Okay, we've got that. So what we basically do then is we take the address in binary and the subnet mask in binary, and we do what's called a Boolean operation called AND, where there's only really a couple of different ways we can get an answer. So if we have a 1 in the address and a 1 in the mask, then the result is a 1 down below. So where we have a 1 and a 1, we have a 1. If we have any combination of 0 and 1, so it can only be one or t'other, then we're going to get a 0. If we have a combination of 0 and 0, we have a 0. So we've got 4 possible outcomes. We can have 1 and 1. We can have 0 and 1. We could have, we haven't got it here. Oh, yeah, we've got a 1 and a 0 or a 0 and 0. So they're the 4 different combinations we have. The only combination with an AND operation that ends in a 1 is if both the other conditions are 1. So 1, 1 results in a 1, 1, 1 results in 1, 0 and 1 results in a 0. So that's all code all the way through. We do the same in the next octet. So 1 and 1 is 1, 0 and 1 is 0, so on and so forth. Third octet. Then we get to the last octet and we've now got all zeros. So we now know from our second rule of subnetting that wherever there's a 0, the number above corresponds to the host ID. So where we can see where there's zeros here, we know now that these 8 bits are actually representative of the host ID or the actual device itself. And we already know from here that that value there, 001000001 in decimal is equal to 33. So using the subnet mask, we've been able to deduce that the actual network or street that this device is on is 192.168.200, and then we just fill in the last octet with a 0. So that's a network number, and the host ID is 33. So that's a unique. So what that's saying is this particular device is number 33 on the street 192.168.200. And that's the way you use your subnet masks to then determine what your network and host IDs are. What you probably, hopefully, will have also noticed is that the address is exactly the same as the end result. And that's simply because of the nature of the AND operation and the fact that you've got all ones there. So it basically doesn't change the value of the first part of the equation. So we've got 2 characters where there's a 1, it doesn't change the value from the top. Only a 0 changes the value from the top. So the rule of thumb is a 1 will keep the value the same, a 0 will flip it or turn it to 0. That's IP addressing really quick and in a nutshell. It's probably longer than 10 minutes, so I apologize for that, but that's it in a nutshell. It's so much more in depth than that, but hopefully that gives you a little bit of an understanding. And that's really it for networking. So now, and I'm mindful of time because yeah, we're going way over. We're going to go way over, and I apologize for that. I'll try and get through the cybersecurity stuff as quickly. It's a little bit more simple, so we'll get through it as quickly as we can. But keep any questions coming through. Obviously, we'll queue them up at the end. So cybersecurity. Network security are simply the mechanisms by which network information assets are protected. And it has 3 primary goals: to protect confidentiality, maintain integrity, and assure availability. That's it. Confidentiality, integrity, and availability are your 3 main things you want to protect of all your information assets. We talk about a very simple model at IT Masters in our cybersecurity fundamental subject, and that is the CIA-DAD triad. And all they are is 2 sides of the same coin. So it's like a head and a tail. Around your data, you have these things that you want to protect. So rainy day, you have these things you want to protect over this side. So we have our confidentiality we want to protect, our integrity, and our availability. The attackers or threats that are coming after us want to destroy, deny, and disclose. So destruction is the opposite of integrity. Disclosure is the opposite of confidentiality, and denial is the opposite of availability. So where you have destruction, you don't have integrity. Where you have disclosure, you don't have confidentiality. Where you have denial, you don't have availability. But it is possible for you to have a mix and match. So you might have, say, you might have your availability and confidentiality maintained, but you've had some destruction of data for some reason, either accidental or deliberate, and so therefore you haven't got your integrity. So you can have different components of each in existence at the same time. So security should ensure that users can only perform the tasks they are authorized to do. They can only obtain the information they are authorized to have. They cannot cause damage to data, applications, or the operating environment, either deliberately or accidentally, and that any data exchanges or communications are conducted in a safe and secure manner. And that's really the basis of information security. That's what it's all about. It all centers around that confidentiality, integrity, and availability in whatever context you want to put it. So what are some common attack categories or threats that we might see in typical networks? There are lots. There are lots of them here, and this is definitely not exhaustive. So we have malware, we have ransomware, getting more and more prevalent. We have man-in-the-middle attacks. We have zero-day exploits, which are literally just attacks that have been, found on this particular, have initiated on a particular day. So it's a zero-day attack. We have things like DNS tunneling, cryptojacking, cross-site scripting attacks. Social engineering is a really big one and really is very closely linked to this one over here, phishing. And phishing is a primary type of attack that usually initiates most security incidents. We have SQL injection, we have denial of service, distributed denial of service attacks. Now, all of these are things that we could spend many weeks talking about. And so we're not going to go into any depth of all. Just understand that there are many different types of cyber attacks available. And really this one here, phishing, is the root of many cybersecurity incidents today. Who are the threats? Who are the threat actors? There might be nation states, so government-supported hacking organizations. There might be corporate spies, so industrial espionage. There could be malicious insiders, so that is disgruntled employees who don't like what's going on in the business, and so they want to get back at them in some way, or they might have been paid off by a competitor, for example. There are hacktivists who have different motivations again. So typically nation states and corporate spies are about espionage. Hacktivists are about achieving some sort of social or maybe political goal at a minor political level. We have terrorist groups. I think it's pretty obvious what they're after. And we have hackers who could be in it for any number of reasons. So they might be in it to gain information, to gain a competitive advantage, to try and make money, to steal information, to sell it to someone else, for example. And then we have criminal groups who are primarily involved in attacks to make some sort of asset for themselves, whether it's money, through just stealing information, selling it, through extortion, through the use of ransomware, those sorts of different attack vectors. So there's lots of different ways in which you can potentially be attacked. And that may seem quite scary, but ultimately you have to understand what the risk is. So what the problems are or vulnerabilities are in your network, and what the likelihood that someone is going to actually specifically target you. And then from that, you can decide, okay, is it worth the risk of not doing something, or do we have to spend money on protecting ourselves? Cybersecurity for SMEs, subject matter experts. Aha. So phishing attacks. It's not subject matter, it's small to medium enterprise. I was just joshing around. So phishing attacks are most common incident for small to medium enterprise. Phishing is where it's at the moment, because it allows them to get a foothold into do whatever else they want to do. So web-based attacks, general malware, as a malicious insider or denial of service all lead on from phishing attacks. So this is number one. It could be via email, it could be via social media, so smishing, could be over voice, so vishing. It could be targeted to big corporate, to powerful corporate people like CEOs, CIOs, CFOs. So that's called whaling. Okay, that's targeting. Spear phishing is where you target a particular individual. So there's lots of types of phishing, but phishing in general is just trying to get some information out of someone that you shouldn't have by some means, whether that's sending them an email, a phone call, social engineering, dropping a note on their desk, giving them a USB key with a document on it, all sorts of different ways it can be implemented. So let's just turn that off and let's just have a quick look at this, what phishing is in a little bit more detail. Just let me make sure that I'm share. Haha, I'm not, so I better share that. Share the sound and let me start that.
Phishing is a game of deception. Phishing is a fraudulent method of gathering sensitive information such as usernames, passwords, and credit card details using deceptive emails and websites. In a phishing attack, the attackers pretend to be a trusted entity and tricks the user into opening an email, text, or instant message. Next, the user is enticed into downloading an attachment, clicking a link, or providing sensitive information such as login credentials. How can you spot a phishing attack? Let us take a look at 4 common types of phishing attacks. Email-based phishing. Let us analyze this email. Here, the subject is a psychological ploy to create anxiety, which can trigger an immediate response. The sender email ID isn't a genuine one. The logo is inserted to create a sense of trust. There is a call to action followed by a link. The next time an email tries to rush you into downloading an attachment, clicking a link, or sharing sensitive information, look out for these signs. Text-based phishing or smishing. Like email-based phishing, text-based phishing uses psychological ploys to trigger a reaction, in this case clicking the link. Phone-based phishing or vishing. Like other forms of phishing attacks, phone-based phishing too uses psychological ploys. How can you guard yourselves from phishing attacks? The solution is simple. Always be alert. Ask yourself, is this email, text message or phone call genuine? Always check for the phishing indicators. Remember, if in doubt, do not respond and always reach out to your cybersecurity support team for assistance.
All right, so the interesting thing about that, the thing to probably get hammered home most importantly is that all phishing attempts will have a sense of urgency about them. So they will want you to do something right now. You must reply right now. They often come from sources that seem legitimate, but you need to scratch the surface and really look at things carefully. So if it's unexpected, if you're not expecting a particular email or contact from someone and it's based on urgency and you've got to respond now and you haven't got time to do anything else, just take time to think about whether it's legitimate or not. Always ask the question. So if, for example, you get an email that seemingly comes from your boss and they're asking you to go and pay this big invoice for something and you're not expecting it, and for whatever reason you can't get into contact with them, just hang on a minute until you can confirm it with someone that might know. So don't just respond to everything and assuming it's safe, because these phishing attacks can be very sophisticated and very convincing. In many cases, however, the common phishing attacks that you'll get to your email box at home will be very poorly worded, or they'll have lots of capitals in them. They'll be written like someone's shouting at you. But again, they will have a sense of urgency about them. You must act today. They will often offer you something small in return for something, or they'll offer you something, significant in return for something small. And that's the way they sort of get you to start to interact with them. So they might say, if you send us $5 postage and handling, we will send you this new iPhone 13 or something like that. It seems like, oh, well, it's only $5, but if they send that out to 10 million people, and 1% of those people, so 100,000 reply, and then of that 100,000, they get 10,000 people to send them $5, then they've made $50,000 for very little work. So it's a game. You've got to be really careful about these phishing emails, because they are becoming more and more common, and they offer you all sorts of things. General rule of thumb is, if it seems too good to be true, it probably isn't. Okay, the next, it's interesting. Now, this video is also, both these videos are up on Moodle. This is an interesting one, quite a humorous one, which shows us what the main problem is really in security, is that it's actually human error. So have a look at this one. This is a little bit more entertaining.
Today is perfect for a security breach. Click on everything, that's the lesson I teach. There's no time to think, just click on the link, and then wait and see what happens. Hello there. Ever wonder who's responsible for most security breaches? Well, you're looking at them. What do you say we go get in some people's heads? See if we can't get them to make some questionable decisions. Sound like fun? For me, it's just another day at the office. When it comes to security, you're going to hear a lot about what you should and should not do. All those mixed messages can get confusing, which is why I'm here to keep security simple. Let's start with passwords.
Due to a recent security breach, we need everyone to change their passwords.
Again?
Yeah.
This is so hard.
Remember to keep your password simple. Doug, you use the same password for everything. Just go with what you know. Do you have a favorite password that you use for personal stuff? Good news. There's nothing wrong with using the same thing at work. Also, remember to keep your password obvious.
Hey, remember, don't make your password obvious. Right? Anything predictable is easy to hack.
And easy to remember. Sure, the hackers might get it, but you won't forget it.
Okay, I might just pause it there, because I'm just mindful of keeping it tonight for time. But as you can see, that's a bit of a parody around security. So when you watch that video, it's available on Moodle for you. Don't listen to what this fellow here, named Human Error, says, because he's giving you the wrong information. So it's a bit of an attempt at levity. That comes from a company called Mimecast, and it's part of their security awareness training platform. All right, so I'll move on, but that video is available for you on Moodle.
Use your.
All right, so host network and design concept. So this is, in this section, we're going to quickly have a look at some of the concepts, basics around keeping your hosts secure, so your desktop, servers, workstations, and how to build or how to implement some tools that will help you keep your network a little safer. It's not going to be exhaustive. It's going to be the fundamental objects and tools that you would use and that we talk about when you come when we do the cybersecurity fundamentals subject as part of our postgraduate programs. So defense in depth is the first definition we need to know. So that's an information assurance concept in which multiple layers of security controls, which is a defense, are placed throughout an information technology system. So it simply builds on the idea advocated by Sun Tzu, who was a Chinese philosopher and warrior from many, many years ago, in that the idea that multiple layers are harder to defeat. So if you think of a medieval castle with the actual where the king or queen lived, built in the center of that castle, then the wall around that part of it, and then all the peasants would live outside that wall, and then there would be a bigger wall around them, and then there would be a moat with a drawbridge. All of those are multiple layers, so it makes it more difficult to get to the king and queen than it would be that if they just lived in a little wooden hut out in the paddocks. So the more layers you have, the more difficult it is to defeat. And so when we talk about security design, we try to implement multiple layers. Now, a closely associated principle is the idea of the perimeter. The perimeter in that example of the castle with the moat around it is the moat. Okay, that's a perimeter defense. That's the most outlying defense system, the moat. And so if you take that to a digital analogy or a network analogy, you may say, okay, well, you know, the point or the demarcation point of our perimeter is where we connect to the internet, because, you know, we're afraid of the big bad guys out on the internet, but we don't have to worry too much about anyone inside our network because it's all safe and secure. We have an elevated level of trust, and that's okay. But that is completely wrong. Okay, the concept of a perimeter has changed radically over the last 10, 15 years. So no longer is it just representative of the barrier between the internet and your internal network, because we now have wireless and mobile technologies that can connect from outside locations through the air. So we can't see how these devices are coming in physically. They just appear there. And so we have to have a perimeter or edge, if you like, a buffer between wireless connections and our internal network as well. And what about VPNs, virtual private networks? So people who are coming out from the internet using an encrypted tunnel to come into our networks. We can't control their endpoint. So it may be that it becomes compromised and then it becomes a risk to our network. We might have a wide area network with extranet partners, people we do business with coming in through our wide area network. We need a perimeter around them as well to prevent them from impacting our systems. So really a security perimeter has to exist wherever you go from a more trusted network to a less trusted network, whatever that may mean. So whether that's two departments within your environment that don't necessarily interchange information or not necessarily trust each other, but there's a lower level of trust between the two, digital trust, you would have a perimeter between them. So there could be multiple perimeters, there could be a single perimeter, but there could be many within your network. So it's not just the protection between you and the outside world anymore. So you've got to ask a question, where does your perimeter lay? So where are you going to place your security devices to secure the parts of your network that need to be secure from everywhere else, including internal and external threats? You have to know where that perimeter is in order to be able to defend it. One of the things we talk a lot about in cybersecurity fundamentals is the concept of a baseline. You have to understand what is normal in your network or what is allowable in your network before you can decide what is abnormal or not allowed. So you have to have some ground basic rules set up first, or basic idea of how your network should look before you can decide how you're going to protect it against numerous other attack vectors and threat actors. So implementing host security, we've got to remember that our security chain is only as strong as the weakest link. And so we have to make sure that we have some sort of security on all our individual systems. So our desktops, our servers, our mobile devices, our laptops, maybe printers, maybe other devices as well, depending on what we've got deployed. And it's really important to understand, of course, though, that there's a continuum. So there's a balance between how much security you provide compared to how much usability you want a system to have. So the more usable a system is, generally the less secure it is. The more secure it is, the less usable it becomes. So the less you can do on it because things are tied up really tightly. And generally, most businesses will exist somewhere in the middle there where they need adequate security to maintain their confidentiality, integrity, and availability, but not so much that their users can't perform their day-to-day tasks. So in terms of host security, we can use personal firewalls. They're most useful for desktops and laptops. They come for Windows, Linux in forms of wrappers, so different mechanisms of installing these firewalls. Whereas servers are often protected by an enterprise firewall, which is much like the hardware we were talking about before, switches and routers. So it looks a bit like that, although they can also exist in a virtualized platform now as well. The reason we don't often put personal firewalls on servers is because servers are often very busy providing lots of different users access to their applications. And so having a firewall on that, interrogating all that information that's coming into the server to see if there's anything wrong with it, can sometimes be too much of an overhead in performance. We can also use host intrusion detection systems. So these are almost like a firewall on steroids. So they start to do behavior analysis of the information that comes into your systems to determine whether there's any fingerprints, if you like, that look like some sort of malware or some sort of well-known attack. The problem with a host IDS is if you don't baseline them properly, so you don't teach them what is normal in your network, then they can come up with what are called false positives. So that is, they say that there's something wrong with the information coming into your server and they cut it off when in fact there's actually nothing wrong with it. So that's a false positive. A false negative is when they let something in, but it's actually bad. Okay, so a false positive is less dangerous than a false negative, but there's still, we want to provide a balance between the two. We can also use, and we should always use, some form of malware antivirus protection. So that'll include things like patch management, making sure that our systems are patched up to date. We have antivirus, anti-spam, spyware, and adware, all those sorts of tools installed to prevent that from sort of happening. We have phishing filters, pop-up blockers, safe web surfing practices. All of those can be used really easily and implemented really easily in a standalone or an enterprise environment. We can also use principles of device security. So that we're talking about mainly physical there. So stop people from walking off with your laptop. So we can literally have them chained or locked to a desk if we need to, desktops, laptops, whatever devices. We want to stop prying eyes. So what that means is talking about things like placing your desks or screens in such an orientation that people from the outside world or people, coming into your building from the outside world can't just walk past and see what you're doing on your screen. Because if it's confidential, they might see it and therefore they have information that they shouldn't have. So therefore your confidentiality is compromised. And of course, theft prevention to stop devices walking out the doors. And just a really quick anecdote on that. Many years ago, I did a deployment of new IP telephony handsets to a building, 500 of them. And it was before the builders had actually handed over the building to the organization I was working for. We rolled them out on the Friday and we came back in on the Monday morning and 300 of them were gone. No cameras or anything to tell who that was, but someone had come in and pinched 300 of those 500 phones. They weren't going to be any use to them because unless they were selling them off to someone, they couldn't use them at home, obviously, because they were Cisco IP phones. But anyway, that's an example of a big mistake we made in that sort of area. Data security includes things like encryption. So disk encryption on your laptops or encryption during transmission. Screen locks, so locking your keyboard when you walk away for a period of time. Password protection, so making sure you've got a decent password on your device and you regularly lock it and use it. You might use biometrics, so thumb scans, palm prints, retina scans, all those things that you see in the movies. And file and share permissions, okay, which are typically implemented in an enterprise client-server environment rather than a peer-to-peer environment. And then we have our network security devices, so firewalls, which are used to simply filter packets or filter traffic on some set criteria. So that is, how do you want to treat the traffic as it comes into your network? You determine that, you place a policy on a firewall to do what you want it to do. And they're simply used to designed to prevent bad traffic from entering your network or from transiting across your network or going between departments, depending on where your perimeter is, okay? So everywhere you have a more protected network, you want to have a firewall or at least some sort of control point like a firewall between it and everything else. Of course, firewalls can be software-based, they can be hardware-based, they can even be virtualized now as well. Lots of different options, lots of different types you can use. Regardless of the configuration of a firewall, the location is the most important factor. So it doesn't matter how strong your firewall is or how good your rule base is on your firewall. If you place it in the wrong spot, then all you're doing is giving yourself a false sense of security and things don't work. All communications in and out of a more secure network or more secure part of your network should flow through a firewall ideally. And we need to be very explicit with what we let in and out. So we only allow authorized traffic in. So traffic that we expect and want to come in. Everything else is blocked. So we don't like to, and I've seen it millions of times, well, not literally, but figuratively millions of times where customers will, you'll build a firewall for a customer, you'll hand it over and you'll say, what rules would you like to put on? Oh, we don't know, just put a rule in that lets anything past. Yeah, okay, we don't like doing that, but we'll do it for you. That's what the customer's requested. And then you go back and look at it 2-3 months down the track and they've done nothing. And so everything is coming in and out of their network. They think they're secure because they've got a firewall, but it's just folly, doesn't work. It's also important for a firewall to be able to recognize, resist, and log attacks that are directed at it. Because obviously if it can't and it gets attacked and it goes down, then it's not going to be very useful to you as a security device. We also have intrusion detection systems that work at a network layer. So at the network level rather than at the host layer. And these monitor and identify specific malicious traffic based on either some sort of anomaly, so some sort of behavior or some sort of signature. And as you see in the next slide, they can do it either actively or passively. So actively means when they see some bad traffic, they'll actually stop it or try to prevent it in some way, as well as alerting you that something's going on. If they're passive, they will simply only try to log it and they might alert you, but they're not going to actually actively try to stop it. So anything, and again, this is really important to have a baseline in effect for your intrusion detection system. So you've got to teach it what is normal and expected in your network in order to be able to detect what is abnormal or unexpected. And there are lots of things, different things that IDS can detect, including these here, not an exhaustive list. As I said, they can be based on anomaly, which looks at unusual behavior or changes in behavior that's expected. Or they can use like an antivirus package, they can use a signature. So matching specific knowledge profiles to traffic patterns. And they can be active and passive, as I've already explained. A host intrusion detection system, or HIDS, is the one that we install on a host device. It installs it as a service, and it will intercept any traffic that comes into that device before any other processor. So before the processor, the CPU or the operating system gets it. And they're really, really good at examining the interactions between different applications. But they do take up processing power and memory on your devices. So if you've got a heavily utilized device like a server, they might not be so good. They can run in real-time mode, which is always monitoring, looking, cleaning, spotting traffic as it comes through, attacks as they come through, or they can be snapshot, where they will take a picture, if you like an image of what happens at a known point in time. So this is our baseline snapshot. And then sometime in the future, it might be an hour, might be a day, it might be a week, it might be a month, however you configure it. Shorter is better generally. It will take another snapshot and it will compare the baseline with the current snapshot to see if there's anything unusual or unexpected that might have happened. There's also the NIDS, or network intrusion detection systems, and these are a different economy of scale. So these are used to protect whole networks, and these are generally the most popular form of IDS. They capture and analyze live traffic as it goes across your network, and they're designed to protect more than one device at a time. So they'll protect whole segments of your network or your entire network. Again, it's really important to configure them tightly and correctly based on your own baseline rather than just let them go out in the wild. So generally you'll put them in for a little while, let them monitor, teach them through the control panel or the administration tool what's good and what's bad, and then over a period of time the intrusion detection system engine will learn and it will start to dynamically interpret traffic as it comes through the network. So which one should you use? Well, it depends. Depends on what you want to protect. Do you want to protect a host, an individual device, a subnet, or an entire network? So if it's a host, you would use a host intrusion detection system. If it's a subnet or an entire network, you would use a network intrusion detection system. So do you provide network services to customers, or are you just an enterprise customer yourself? So the sizing of your IDS and placement might be different. What is your network topology? Typically, it's going to be a star. But you need to place them judiciously and intelligently. Like a firewall, if you put them in the wrong spot, they're not going to give you the right protection or the right information. And are you going to deploy them as an anomaly detection, so based on changes in behavior, or are you going to use signature? Or you can use both, one or the other. You don't have to use one or the other, you can use both. The point is with network design and placing all of these tools is that there is really one solution to a problem, but there is often a best solution. And that is going to depend on the goals that you're trying to meet when you're doing your secure design. Other tools that you can use include IP subnetting, okay, which we briefly talked on earlier, because it helps you to decrease network traffic on specific subnets because the traffic is then segmented or split up by subnet. It allows you some flexibility in being able to expand or shrink parts of your network by changing the subnet. It provides ease of troubleshooting because each of the subnets will be assigned to a particular department or area or geographic location or work group. And so you'd know that when that subnet is having trouble, then it's something within that particular work group, geographic area, office level, whatever. It allows you to be more efficient in the utilization of your available addresses because generally you'll only be assigned a certain amount from a service provider, or if you're using internal addresses, you'll only have access to a few or a small range. And so you need to be able to intelligently use them to make sure that all the hosts you need to have connection. Also reduces the impact on routers because it reduces the amount of traffic inside each network and therefore the amount of noisy traffic or broadcast traffic that's generated. And you can actually use them to reflect the actual network topology or function so that you can use them almost as a documentation tool as well. This is an example of some subnetting here, an example of subnetting here. So we've got subnet 1 connected to this router. We have a tiny subnet in here connecting the two routers, another subnet here, another subnet there. And each one will have a slightly different subnet mask as defined by the / notation based on the number of hosts that are expected to be in that particular network. Okay, so this has got a /25, which means it's got 25 bits for the network and it's got 7 bits for the hosts. This one's got 21, so 21 for the network and 11 for the host, so it's going to have more hosts. And in this one, this is tiny, so it's got 30 bits for the network and only 2 bits for the host, which gives us 4 combinations, which effectively is only 2 addresses you can use. You can also use VLANs, which are virtual LANs. Now these aren't used by routers so much, they're used by switches, but they are generally aligned and analogous and related to IP subnets. So they are very different, but they are similar. They're almost like two sides of the same coin, if I can use that same phrase again. A VLAN will allow scattered users throughout your organization to be logically grouped together, even though they may be in physical different locations connected to physically different switches. And this, like IP subnetting, can reduce the network traffic as well. So this is an example of some VLANs. So we've got a router up the top, we've got our 3 switches, and you can see we have 3 devices from the engineering department, 1 on each switch, but we have them logically grouped together in the engineering VLAN. We have 3 logically grouped together in the marketing VLAN and 3 logically grouped in the accounting VLAN. So even though they're on separate switches, they are logically grouped together. And if we have a look at how that then equates to our subnets, what we would have is this is sort of similar to set up to this one here. It's just expanded on a little bit. So each of these colored ellipses represents a VLAN, and each of those VLANs is assigned a different IP subnet. And so you can see there's a relationship and a correlation between a VLAN and an IP subnet, even though they're slightly different. We can also use things called a DMZ, a demilitarized zone. And again, these are another military concept, as not founded by Sun Shui, but they are still a military concept that he spoke about. They're used extensively in the modern world, and they basically provide a little separate partner network that sits outside the secure perimeter. So it's a less trusted environment that allows people from external networks to come in and get access to your services without letting them all the way into your network. So the outside users on the internet can access the DMZ, but they can't get through to your internal network. And if we look at that in a diagram, this is what it looks like. So we've got multiple firewalls here, 3 firewalls. We have a web server DMZ where we have a proxy server. The internet, let's draw that up there. So our internet clients come in through here. They go through the first firewall. They go to the web DMZ. If they need to get to one of the application servers, they would go through the second firewall into this DMZ and branch off to whichever server they need to get to. But they're not going to be able to get past this internal firewall because we've got rules on that that says, no, 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 you can't come in from the outside. But what they can do is they can come into the proxy server. So if I just erase that, they can come into the proxy server, ask the proxy server to go inside the network on their behalf, and then the proxy server can go into one of these servers, and then one of these servers can potentially go inside on their behalf. But there is a logical disconnection between the real person out here and this server in here. So they never actually get into there. It's all hidden away behind these firewalls. And that's the concept of the DMZ. So yes, it's a less trusted network. So this one is less trusted. This one is slightly more trusted. This is most trusted. But they are an area, simply an area, a zone of your network that the outside world can come into. Another tool you can use is network access or network admission control. And what this does is when a device tries to connect to your network, the network admission control system will examine the status of the user. So it'll verify the user through authentication credentials, and it will verify the status of that device based on a policy that you configure. So your policy might say, well, if you're a VPN client, you're coming into a network, you have to have this version of operating system and it has to be patched to this level, and you have to have this antivirus solution installed as an example. And if you don't, then you're basically deemed to be an unhealthy client. And that unhealthy client will be directed to the remediation network, where it might download a patch, it might download an antivirus signature to remediate the things that are wrong with it. Once that remediation is done, so the antivirus is updated, the device is patched, then the network admission control system will again examine it, and it'll say, okay, now you're healthy, your fixes have been applied, so I will now let you join the private network and come inside. So that's the base, the real fundamentals of how a network access or admission control system will work. And then last of all, we have zero trust network admission control. And this is where we basically build the concept of zero trust. In other words, we don't trust anything. Everything is managed by network admission control. And that's a whole, that's a topic for a whole MOOC, a whole subject, probably a whole course all on top of that. So that's really what I wanted to end up on. So hopefully that's given you some basic idea about cybersecurity fundamentals and how complex the area of cybersecurity is, because even at this fundamental level, there's quite a lot of complexity built in, and there might be quite a lot of questions that you have coming out of this, and that's completely okay and completely expected. The same with networking as well. We really just scratched the surface of what's there, so there's a lot more underneath it. But hopefully all of that put together with what we spoke about last week will give you a good basis from which to move forward in your career transition or education or whatever it is that you are doing. So now I guess we can have a look at some questions if there's anything there, Shane. I'm sure there is. What have we got?
There's just there's just one or two, Matt. Before I go into the questions, and we will close questions in a minute because we're already running, as everybody imagined, way behind time, and we'd encourage people to put their extra questions into the forums that are on the Moodle site on learn.itmasters.edu.au. Couple of things. There is a survey coming out at the end of this session that we'd ask you to fill in, just to give us a bit of feedback about what's gone on. And while we're talking about surveys, I just thought I would mention by the by that we are looking currently at options on the Internet of Things as a course. And so we've sent a survey to everybody in our database who might have got it. We'd love you to fill that in, and Kit will actually stick the URL for that in the chat as well. She's just chucked the survey chat, the survey for this course in the chat, and she will take our Survey Monkey one in there as well. So yes, so let's start with some questions. Let's go. There's 20 odd here. We'll probably get through about half them, I realistically think, before we run out of time. What are port numbers? Let's start with that one from Ray.
Okay, port numbers is probably really beyond the scope of what we want to talk about in fundamentals, but port numbers are the next layer up. When I was talking about the IP addressing being, the street address and the street number, the port address is basically indicative of windows and doors on your house. So if you've got a server with an IP address, it's on a specific network or street. So the network ID, it's got its own unique number on that street or host ID, and then the ports are the windows and doors that allow you access to the applications that it's providing. So whether it be web server, mail server, FTP server, or whatever else.
So, and some each apps use different ports, don't they, at various different times?
Yes, they will, and all there's what's called well-known ports and ephemeral ports. So well-known ports are those that are registered for specific types of applications. So, for example, HTTP or web server will use port 80. That's a very easy typical example. But there are many ports that are registered, and then there's others that can be used dynamically depending on the application's communication requirements.
Any port in a storm. Apologies for that joke.
Nice.
What are proxies, Alvin?
So a proxy server is simply a device that will do something on your behalf. So if I want to go out to the internet, I might send a request to a proxy server and ask it to go and retrieve information from a website on my behalf, and it will do that on my behalf. And what it allows you to do is hide your presence behind it so that your real device itself can't be seen from the outside world. So it's a protective mechanism.
Excellent. Hardy, and we're whipping through the questions tonight. I apologize for that a little bit. We'll probably do it a little bit faster than usual. Hardy asks, do you recommend practicing zero trust or using the baseline and context-based security control?
The answer to any design question is it depends. So it has to depend on what you are trying to achieve. The zero trust is probably more suited to larger organizations, larger scale organizations, whereas the other approach can be used by anyone. More complexity in zero trust NAC, but a lot more features, a lot more scalability, a lot more portability from place to place. So you can have remote sites, you can have remote users all over the world. The base model, though, will work anywhere.
Hardy also asks any tips about changing the security culture in an organization?
Well, that's a massive question, but just to keep it simple, really, there's no doubt that security culture is extremely important. I often talk about a human firewall, and that's really your end users. They are the first port of call in protecting your network. So if your users don't have any awareness or security culture ingrained in your organization, they'll be clicking on all sorts of phishing things all over the place, like the guy in that video I was showing you before. The best way to do that is you need to implement some sort of security awareness training. Now that can either be developed in-house, or there are many vendors that can provide it to you externally. So Mimecast is one, KnowBe4, Friendly Phishing, SANS, there's lots of them out there. So if you were to do a Google search for security awareness training, you'll be able to find a vendor that will assist you in that, and they can do things like those videos that I was showing you. There'll be posters, there'll be phishing campaigns where they'll send pretend phishing emails in to click on things, and they can be very, very sophisticated. Obviously, the more money you pay, the more sophisticated and more useful it will be. But over time, usually minimum of 12 to 18 months, you will start to build a security culture within your organization because your users become more aware of what the risks are and what they look like.
Right. Is client-server topology safer from a cybersecurity perspective?
I wouldn't necessarily say safer. It depends on what sort of security tools you've got on your individual stations. So if you've just got a Windows, a group of Windows devices talking to each other straight out of the box, then they're not going to be very safe or secure. But if you've got a client server deployment as well, that is directly connected to the internet and it's just out of the box, and that's not very safe either. The reason client server probably has that feeling of being more safe is that it's generally deployed in an environment where you'll have a number of different network security tools at your disposal as well. But in terms of, it's more around the client server versus peer-to-peer is really more around the scalability and performance from a network perspective rather than a security perspective.
Okay, a couple of questions on networks, if we can cast our minds back to that. Three or four sort of very similar ones. Abdullah is asking, I've used Router OS, and when I went to connect, I use a MAC address instead of an IP. So the question is, how could we perform such a connection? For instance, is there something like ICMP in the Ethernet MAC?
Again, so we're asking things that are really way outside the scope of a fundamental course. But the answer is yes. So basically, in being able to communicate across to a router, you need to have one of two things. So Router OS, I think, was the one you were talking about. Was it Router OS?
Yes.
Okay,
yes,
I think it was,
right.
yeah. Okay, so it has the ability, yes, you can connect via a MAC address. So a MAC address is a hardware address that I was talking about with the hexadecimal. There is a relationship between, there's not a linkage between an IP address and a MAC address. A MAC address is completely unique and physically programmed into your device at manufacture. An IP address is something that you statically give it afterwards. But on a single device that has an IP address and a MAC address, they are like two sides of the same coin, to repeat that phrase yet again. So they are linked inextricably on that device. And so in order to be able to get to a router, you either have to know the IP address or the MAC address. Now, if you just know the IP address, your computer will go and find the MAC address of that router before you can connect to it anyway. And that's a whole conversation around the OSI model and the construction of Ethernet packets that is, yeah, way outside the scope of what we're sort of talking about. But if you want to put, if you want to expand on that, we can do that in the discussion forums.
Absolutely, and I'll keep pointing people at the discussion forums because we're down to the last couple of questions, and 9:30 is, I think, our absolute dead time. I know somebody wanted to change an appointment because it's a long way away from where we started. Somebody has asked, what's the best way to program or use to essentially to set up a file server so that you can VPN remotely and use the files?
It's a design question, so the answer is
it depends.
There are many ways in which you can do it, and it depends on how many users you want to come in via the VPN, whether you want them to be always on or just to be, ad hoc. Do you want them to connect from other sites of yours, or are they going to be connecting through internet cafes? What sort of speeds do you want them to have? What do they need access to? You can use IPsec-based VPNs, which use encryption. You can use SSL-based VPNs, which also use encryption, but in a different way. They're a little bit more lightweight. There is no one way that's better than another. It depends on what you want to, what you're trying to achieve. So again, that is something that we can really discuss in more depth in the discussion forums. If you want to post up some scenarios there, we can answer them there.
That's very good of you. And we're down to the last question because you've actually answered quite a few of the other ones by the by in answering the ones that we've been asking. Alvin asks, can ports be infiltrated by malicious actors? And I'm assuming the answer is yes.
Absolutely, it is. That is exactly what they're trying to target. So when they do enumeration or vulnerability scanning and they go and they start tapping on your network to see what's there, they are specifically looking for IP addresses that are active, and then more importantly, what ports are active, because that then tells them what applications you're running on your server, and that then tells them or allows them to research what vulnerabilities might exist in those applications that they can exploit, get into your network, and then most importantly, because when an attacker gets into your network, there's two things they want to do. They want to either elevate their rights, so get from being a nobody to being God mode. And then they want to move laterally. So they want to move off that initial attack site to get further into the network to see what they can find for whatever motivates them. So absolutely, they attack ports. That is typically what they're looking for.
Excellent. Well, I think that wraps us up for tonight, Matt. You've packed a lot in. I reckon we could have easily split this into two with the amount of stuff that you've been able to get through tonight. It's huge.
Yeah, it is. And I do sincerely apologise to my colleagues and all of you out there who are still game enough to be listening. I like to try and give a lot, and there's a lot to digest, but I hope everyone's got something out of it, and I hope it's been worthwhile.
I reckon everybody who goes now into cybersecurity fundamentals that you teach will really have a good basis to work from as well.
Oh, they certainly will. Certainly will.
So again, thank you everybody for coming along. Really appreciate that you've been with us this evening and also on YouTube. We did notice that while there was, hundreds of people listening to the last webinar, there are literally thousands and thousands of people who have already watched our YouTube video of it. So we encourage you all to tell your friends and get the YouTube one out and have a look at that as well. I'd also like to remind you that there is a survey link that's been sent around for to give us some feedback about Matt's performance and the course in general. There is also a survey that we're doing about the Internet of Things just separately for anybody who's interested in telling us what they think they'd like to learn about the Internet of Things, because it's a very busy area. And finally, on this relatively late evening in Melbourne, I'd like to say thank you so much to Kit and to Lily, who have been madly dropping things into the chat continuously tonight.
Yes, well done, bravo.
And also, I've just been reminded, and that's why I thank them, because they know how to tell me what to do. There is no exam for this course. There is a quiz after this week, but no formal exam, and we won't be issuing certificates for this course like we do with our normal ones, specifically because this course is not qualifying for credit as most of our other free short courses do. If you do 3 of our normal short courses, you're able to get credit for one of our subjects. With this course, because it's an introductory one, we don't offer credit for it. Therefore, there's no certificate and no formal exam, but there is a quiz in the Moodle that you can do and enjoy. So yes, while I go back to now saying thank you and good night to Kit and Lily, and double thank you for reminding me about that, Kit. And a special huge thank you to you, Matt, for spending all your time setting all this up and telling us all about networks and cybersecurity.
No, most welcome, Shane, and thank you to you for a sterling job as our MC. Bravo, my friend.
It's all fun. Anyway, good night, everyone, and good luck.